There's a single number that really holds the key to unlocking the full potential of our soils. It's a concept that pretty much governs everything from how available nutrients are to the actual toxicity of the ground beneath our feet. We're talking about soil pH, the true master variable in agriculture. So, if I asked you, what is the single most important number in all of agriculture? I mean, if you had to pick just one single metric to understand the health and potential of a piece of farmland, what would you choose? It's not yield, it's not rainfall, it's something way more fundamental. That number is 6.5. Now, this isn't just some random figure. It represents the ideal pH for most crops. It's that sweet spot where that incredibly complex world under our feet just clicks. Everything falls into place, allowing life to truly flourish. Getting your soil to this number is one of the most powerful things you can do.
Okay, so let's really dive into this. To understand why 6.5 is so magical, we first have to get a really solid grip on what soil pH actually is.
At its core, soil pH is simply a measurement of how acidic or alkaline your soil is. It's all based on the concentration of hydrogen ions floating around in the soil's water. We measure it on a scale from 1 to 14. A pH of 7, that's perfectly neutral. Anything below 7 is acidic, which just means there are more hydrogen ions. And anything above 7 is alkaline or basic.
So it really comes down to this simple balance. Think of it like a seesaw. On one side, you've got your acidic soils with a whole bunch of hydrogen ions. This is super common in places with high rainfall, where basic nutrients get washed or leached away. On the other side, you have alkaline soils, which you tend to find in drier regions with an excess of hydroxyl ions. This constant chemical tug-of-war dictates the entire soil environment.
Which brings us to the big question. Why should you care? I mean, why does this one number matter so much? Well, because for a plant, pH isn't just a number. It's a matter of life and death.
The best way to think about it is like this. Plants need conditions to be just right. They live and thrive in what we can call a pH Goldilocks zone. If it's too acidic, they struggle. If it's too alkaline, they suffer. For them to do well, the chemistry has to be perfect. And this chart? Wow. This chart is the key to understanding everything. It perfectly visualizes that Goldilocks zone. Each of these colored bands represents a different essential nutrient. And the wider the band, the more available that nutrient is to the plant. Now, look closely at that sweet spot, that pH range between, say, 5.5 and 6.5. Do you see how almost every single band is at or near its widest point? This is the zone. This is where the soil unlocks its entire pantry for the plant to eat.
But the moment we stray outside this zone, things start to go wrong and fast. In highly acidic soils, we're talking below a pH of 5.5, really important nutrients like phosphorus and calcium get chemically locked up. They're there, but they're completely unavailable to the plant. And what's worse, toxic aluminum gets released from the clay, and it literally poisons the plant roots. On the flip side, in really alkaline soils, crucial micronutrients like iron and manganese just become insoluble. The plant simply can't absorb them. Either way you slice it, the plant starves.
Now, here's the thing. Soil pH isn't some static number that never changes. Our management practices, the things we do every year, have a huge long-term impact. So let's look at one of the most common inputs we use, nitrogen fertilizer. And it turns out not all nitrogen fertilizers are created equal when it comes to pH. Not even close. If you use an ammonium-based fertilizer, you are signing up for a long-term acidifying effect on your soil. But if you use a nitrate-based one, you can actually cause a temporary increase in soil pH. Understanding this difference is absolutely critical if you want to manage your soil health for the long haul. So how does this whole acidification thing actually happen? Well, it's pretty simple. When you apply an ammonium-based fertilizer, the microbes in the soil get to work. They start a process called nitrification. Basically, they convert that ammonium into nitrate, which is the form that most plants actually prefer. But, and this is the most important part, there's a byproduct to this completely natural conversion, the release of hydrogen ions. And as we now know, more hydrogen ions means a lower pH and more acidic soil. Over years and years of application, this really adds up. Okay, so we get the problem and we see how we might be contributing to it. The next logical step is diagnosis. How do we figure out how to actually fix an acidic soil? And, well, it's not quite as simple as just measuring the pH. To get a real diagnosis, Agronomists use a special test called a buffer pH test, and this is way more revealing than just testing the pH in water. See, the water test only measures the active acidity that's floating around, but the buffer test, it measures the reserve acidity. That's all the hydrogen and aluminum ions that are literally clinging to the soil particles themselves. It's like the soil's hidden bank account of acidity. And it's this reserve that makes the soil resist a change in pH.
And this right here, this is the perfect analogy for what we're talking about. A soil's buffering capacity is its acidity holding capacity. A sandy soil is like a small cup. It doesn't take much to fill it or empty it. It's easy to change the pH. But a heavy clay soil rich in organic matter, that's like a giant barrel. It can hold a massive amount of reserve acidity, and it's going to fight you every step of the way when you try to change its pH. You're going to need a lot more lime to move that needle.
So where does all this buffering power come from? Well, it boils down to three main things. First is something called cation exchange capacity, or CEC. That's basically the soil's ability to hold onto positively charged ions. Second is soil texture. Tiny clay particles have way more holding power than big sand particles. And third is organic matter, which is an absolute powerhouse for CEC, dramatically increasing the soil's ability to buffer against any pH changes.
And this table here really puts some hard numbers to that whole concept. We're looking at how much lime it takes to raise the soil pH by the same half point, from a very acidic 4.0 up to 4.5. Just look at the difference. For a sandy soil with only 5–10% clay, you need 3 tons per hectare. But go down to a heavy clay soil and you need over 4 tons. That's a full 40% more material to get the exact same result. That right there is buffering capacity in action.
All right, so we've defined the problem, we've diagnosed it. Now for the most important part, the prescription. How do we scientifically correct soil acidity? Well, the answer lies in the ancient practice of liming.
The chemistry is actually pretty straightforward. Agricultural lime is usually either calcium carbonate, that's what you find in calcitic lime, or it's a mix of calcium and magnesium carbonate, which is in dolomitic lime. When that lime dissolves in the soil water, the carbonate part gets to work. It finds those excess hydrogen ions that are causing all the acidity, and it neutralizes them, which raises the soil's pH.
But, and this is a big but, not all lime is created equal. The first factor you have to consider is its strength. We measure this as the Calcium Carbonate Equivalent, or CCE. This just compares a material's neutralizing power to pure calcium carbonate, which we set as the baseline at 100%. If you look at the table, you'll see standard limestone is right around 100%, but something like burnt lime can be over 150%, which means it's way more potent and you need less of it to get the job done.
Okay, so strength is factor 1. Factor 2 is speed. And this all comes down to fineness, how finely ground the lime is. Remember, lime is a rock. It has to dissolve to work. The finer the particles are, the more surface area is exposed to the soil and the faster it reacts. A really coarse, gravelly lime might take years and years to fully dissolve, but an ultra-fine product can be 100% available in the very first year.
You know, when you put all of this together, it brings us to a really fundamental lesson. Managing soil pH teaches us that truly productive, healthy soil, it isn't something you just find by chance. It's something you have to understand, you have to diagnose, and you have to actively build, season after season.
So the next time you look at a field, don't just see dirt. See a complex chemical system that has a story to tell. And understanding that story, starting with that one single crucial number, is the first step toward building a more resilient and productive future. So I'll leave you with this. What story is your soil waiting to tell?